Hey everyone. So this is a talk I've given actually for a number of years. It's actually a talk that goes as far back as my original master's work. And so we'll be talking through the work that I presented. In this case, it's 2014, so it's been a while. At the same time, the topics of rank aggregation is just as relevant today, and we've seen a new growth and interest in rank aggregation or ranking, specifically for deep learning tasks. And so I thought it would be helpful to present this work again. Again, it's a long talk. It's going to be about an hour. I know many of you won't make it through the entire talk, and I understand that. But I do recommend that you at least watch the beginnings. To be honest, I think some of the more interesting stuff does rise at the end, but it's not things that you're going to take the code and use tomorrow. They're more approaches or thought processes that drive things forward. Also, I thought it was helpful for my master's students to see what one version of a master's talk looks like at a PhD level. It's a little bit different than what you might expect. My talk by no means is the most technical, but it also isn't the least. So it's somewhere in the middle. The work that I'm going to be presenting is some work that my advisor, Lakhang Lim, really started, and it was under his guise that I started this work. Very interesting stuff, stuff that I haven't found direct application for in my day-to-day work. The algorithms in particular, but the broad thought process about how to think about ranking is absolutely applicable. So without further ado, let's sort of get started with this. Again, I do apologize. It's going to be a while. This was work that I gave in September of 2014, so it's a little bit dated, and I do recommend, you'll see some links during the sort of show notes at the bottom that will give you some information about reading some of the work originally. This talk will also not be the most precise in the sense that I am giving it to a lay audience, a group that hasn't really been thinking about a lot of this very extensively. So, from our perspective, what are we trying to achieve in terms of this whole talk? We're really going to talk about these. We're going to set up the framework of this notion of cardinal versus ordinal rankings. And then we're going to dive into several different algorithms and how they relate to that framework of thinking about cardinal versus ordinal relations. And then we will touch just briefly in my actual talk, master's talk. I went into the details quite deeply here on the applications. In ours, we will just note that they exist because I don't think it's really germane for our discussion. So to start this whole conversation out, the first question we have to ask ourselves is, why are we even thinking about ranking? Where does this topic come from? Why is it worthy of estimation? And from XKCD, we have this notion that we know from the internet today that ranking is something that's done quite extensively. But we know that 5-star ratings are almost impossible to get, and very low ratings are also very low likelihood. So we've realized that we need to adjust our scales, our notion of where scales should happen. And I always recommend to my students that that's something that they look at. There are some research that's done for the optimal number of choices humans can use in terms of making a judgment. Likert scale is one example. For our cases, we see that Likert scale doesn't translate particularly well to the internet as XKCD mocks here. So ranking actually has its rich history. It goes back to the 1700s. Some people you can look up if you want, but it's been around for a long time as we thought about rankings and how they would apply to sort of mathematical analysis. So we also have this notion of an impossibility theorem, the Arrow's impossibility theorem, that we have our own sort of incompleteness theorem, which is an interesting thing. There's a link there or an image from Logic Comics, which if you've never read, you should. It's a great cartoon / what's actually like a graphical novel, but it's worth a read if you're interested in all this stuff. The question is that if you have enough people together and enough disagreement on the ratings, there is no single ranking that is optimal. That is, if we have enough people who have disagreeing rankings in the same room, we cannot get a single rating that maximizes where there's really any agreement. In fact, we can know very little. So the question then becomes, if there exists for any large enough number of individuals a proof that you don't necessarily need to have agreement across the entire group, then should we just give up on ranking as an approach? So the question is really, is it all over? Is that the end of it? And of course, that's not the case. We're going to be talking a lot about this thing called analytic hierarchy process from the 1980s. And this work is done by a professor who doesn't come specifically, I believe he was an economist, but is very much based on work for, in his case, using the principal eigenvalue method. But his interest was really building changes within organizations. So he's really interested in like process management. And so he was interested in the effect that his algorithm and his process for coming to decisions in small groups of people was able to have an impact. And he took credit for relocating a Turkish city, for recommending the release of Nelson Mandela, for addressing the Israeli-Palestinian conflict in terms of helping to have the sides come together, predicting the 1995 Super Bowl correctly, and that British Airways used it to decide its in-flight entertainment system. So Sateh was willing to talk about both the grand effects, but also the very sort of business effects that his process, and it's not just necessarily an algorithm, it was a process that you needed to follow through in order to get that result. But again, my point is just to bring up, we're going to be talking about his work. It comes from the 80s. This is something that is very current, even though ranking and rank aggregation has been going on for a long time. Similarly, Google, this is dated at this point, this $400 billion question. We're far past $4 billion today, but PageRank is actually an application of the same thought process of analytic hierarchy process, the piece from above. So while Sateh turned AHP into a nice tool and a nice academic tool, Google was able to broadcast that to a much larger audience and make it a lot more money. So now, if you're a master's student and you're wondering, is this a topic that's been fully fleshed out? So how well understood is this? Is it completely understood? And to be fair, I think that where I arrived at, my final destination in terms of this whole process was to sort of agree with Robert Christensen. And I at the time in 2014, I was probably very strongly on his side. Today, I'm a little bit less so, but I do understand what he's saying. I tend to agree with it. The key point that he makes, and it's one that's 100% valid, is that the methods abound, but they all suffer from the same drawback, that they're connected to no grand truth. That is, there's no parameter from an underlying probabilistic model, no loss function that would measure the impact of a wrong rating. The second point is really important. When we think about rank aggregation, we're going to say, well, given the fact that we have disagreeing individuals, we're going to bring all their disagreements together in a framework, one way of doing things, and we're going to argue that that framework is best. But we don't have a ground truth for what the optimal ranking is, what the optimal set of ratings are. And so that really causes a problem. Ultimately, that you can leave you seeing differences between different rank aggregation schemes, but not necessarily feeling like there's a clear reason why you should use one or another. So again, let's just talk a little bit about how this works into our regular daily lives. We're using it in voting. The state of Maine uses a ranked choice voting system for president now. We have consensus building. We have crowdsourcing, sports, scoring, ties, data collection methods. There's all different kinds of ways that this could get involved. And we know that, in fact, the academic research related to rank aggregation goes back into a variety of different spaces, eigenvalues, which, again, AHP uses, Google uses. This notion of rank ordering, just literally the rank of the elements. You can use sums and things along those lines to calculate. You can use wavelets. You can use Hodge theory, which is what we'll do with Lekhang Lim's work. Representation theory, Markov chains. There's all kinds of different ways you can do this. So, again, quoting Robert Christensen here, my interest in ranking comes partially from a long-standing gripe about the use, more like abuse, of centrality measures in network analysis. And this is really important. So we know that certain approaches, such as PageRank, can be understood to be centrality metrics. And that actually makes a lot of sense for rankings across websites. But that doesn't necessarily make sense for other types of ranking problems. And that's really what we're going to express today, where we're headed. So again, if we've covered our first section, the categorical and ordinal, now we're going to move into this notion of categorical and ordinal from the introduction. So the first question we have to ask ourselves, and this is actually a moment to slow down the recording and start to think. So don't just put this one in the background. Pay attention now. What does a ranking actually represent? If we have this matrix S with rows 1 and rows 2, we'll call them rater 1 and rater 2, with items T1, T2, and T3, you have to make a decision in your thought process. If I just present you with that matrix S, you have to decide: do you think that rater 1 and rater 2 are in complete disagreement? If I were in class right now, I'd pause, which I won't do because you have a pause button on the screen. But it's a really important point to ask, right? So rater 1 says item 1 is the best item, and rater 1 says item 3 is the worst item. Rater 2 says the exact opposite of that. They say that item 1 is the worst and item 3 is the best. And now you might say, well, I understand that they disagree on item 1 and item 3, but they are in agreement on item 2. What if our items were not 3 elements, but they were 10 elements? If they were 10 elements long and they had the same sort of structure, or what we assume the structure is when we say they're in the reverse, they're in perfectly disagreements, we'd see that the ratings would go from 1 through n, and then n through 1. And there would be very few in the middle, as in this case T2, where they're in agreement. But on the other hand, they really do agree. 100% of the time they agree. If these were gold medals, we'd know that item 1 was ranked first and item 3 was ranked last, or vice versa. And so it's an ambiguous assessment, and it's an ambiguous assessment that we can start to ask questions about. So for those of us who take the categorical approach, that is, we note that the elements, that is, it's not the ordering of elements 1, 2, and 3, rather it's the exact label that's provided to elements 1, 2, and 3. Then we say the raters all agree on the second term. And if we take the ordinal approach, we say, well, in fact, the raters disagree, are in complete disagreement. If I say rank your favorite foods, pizza, coffee, and ice cream, and you give me one ordering, and then you give me the opposite order, we have a colloquial use of the English language that indicates that they're in disagreements. And so what we have is this raw data in the center, this raw data that we're looking at here, can really be interpreted as categories where each value holds, in which case we have this notion of the elements being in agreement, or we can say they completely disagree because of the relationship between the ordering of the elements. And now what's nice about this is we can take these two frameworks and turn them into a matrix representation that's actually quite intuitive. So on the left-hand side, we can say that each element, T1, T2, and T3, are assigned a label 1, 2, or 3. And we can see that by placing T1 gets the label 1, and T2 gets the label 2, T3 gets the label 3 for the first rater. And then we have a second rater who states that, in fact, T1 should receive the label 3, and T2 should receive the label 2, and T3 should receive the label 1. Similarly, with an ordinal classification, we can say that what we're saying here in this ordinal structure is that T1 is greater than or less than T2, right? The number 1 is less than 2, and T2, the number 2, is less than T3. And so now we put in a notion of, is T1 less than T1? Well, it's not. Is T1 less than T2? Yes, it is. Is T1 less than T3? Yes, it is. And we can do the same thing. Now, is T2 less than T1? No, it's not. And is T2 less than T2? No, they're the same. And is T2 less than T3? Yes, it is. It's less by 1. And so now we have a representation on the left-hand side that indicates what our vector, our expression at the top, and we've turned it into a matrix that's very easily interpretable, and we have the reverse down below. And so now we can just use a summation of these matrices. Right? This is important. One of the things I note that can be confusing for our master's students a lot of times is how we take some expression or some notion, some relationship, and we turn it into a matrix, and then we combine those matrices together to get the value. Well, if we add these two together, what's really quite delightful is that we have a very intuitive interpretation. We can take our matrix 1 plus 1. I've normalized here, but 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 1 will be, after its normalization, 0.5. And the value 2 for the center will be a value of 2 here. And this will be 0.5 and 0.5. And this probability interpretation notes exactly what we expressed when we first started thinking about whether or not what we thought this raw data meant. I would say, if I take the interpretation of this categorical approach, that 50% of the time, item T1 gets a rating of 1, and 50% of the time, item T1 gets a rating of 3. And that's exactly what I have. T1 gets a rating of 1 50% of the time, and it gets a rating of 3 50% of the time. Similarly, I would say that T2 always has a probability of receiving a rating of 2 of 1. That is, by just converting this interpretation of the data into two matrices, I can sum them together to come up with a probability matrix. And this probability matrix completely supports our notion of this categorical interpretation of ranking. Now, we can also say that raters completely disagree. And now if I take these two representations where I say the ordering is such and the ordering is such, I can then sum the two together and I get a matrix that's completely empty. Nothing can be learned from this. I have no notion in terms of this binary comparison matrix that the elements are, that there's an ordering that's optimal. The elements in this case are completely in disagreement. it's worth taking a moment to really think about what we've done here. Again, depending upon how much background you have in linear algebra, what we have here is we have an expression in English that we understand, a data set that's unambiguous, and we can interpret that data set in multiple different ways. And depending on how we choose to interpret that data set, we can find a linear algebra transformation. It's very intuitive and very clear and easy to read. And we can just by using a summation come up with a result that actually coincides with what our intuition is. That is, we can describe it in English and we get to the same result as we can do it within linear algebra. And this is one of the great values. Again, if you haven't done a lot of linear algebra at this point, it's one of the great values of where linear algebra really has value. And what's so cool in my mind about this is that when we come up with this y hat, this y bar, where what we're saying is we're getting a matrix that will describe, depending on how we interpret it and how we transform our original data into a vector and then sum it together into a final version that sort of fits with our intuition about how things are working. Okay. Now, it's also worth noting that I've sort of brought in this probability matrix because I've normalized this. We call this a binary comparison because each entry in the matrix corresponds to a binary comparison between element T1 and element T2, element T1 and element T3. Each vector, again, each matrix here represents one rater. Okay, so we've just sort of touched on this idea, this sort of parting in the road. Are we thinking about our rank aggregation as being a probabilistic structure or this binary comparison approach? And these have major changes in terms of the kinds of algorithms we can use. So for my master's work, one of the things that was kind of cool was I got a chance to sort of think about this from the top. We'll start first with this categorical approach. Think of it like a probability, which is what I find most people sort of gravitate to the most naturally. And here what we're going to talk about is this permutation matrix, specifically this notion of bijection flow, and using this Hungarian algorithm, which is a fun algorithm because it goes back to old computer science tools. And then we'll have this ordinal approach that will deal with Hodge rank, which was the approach that my advisor really created, and then this analytical hierarchy process. So the categorical approach. What we're going to do here is we're going to talk a little bit about this progression from a matrix that looks like this to a transition to some type of what's called a bijection. And the bijection really is a set of two sets. You've got a set of elements over here, T1, T2, T3. And then you have a set of rankings, 1, 2, and 3 on the right-hand side. And so what your job is to create a bijection where each element T1 has edges going from T1 to elements 1, 2, and 3 based on the weight of what's in this individual matrix. So you can see T1 here has with 0.50% with 0.5 weight is directed towards the tag of 1. And right here with 0.5 weight, again, we have a direction to the tag of 3. And element T3 down at the bottom similarly has 0.5 weight, 0.5 flow going to element or the rating 1 and 0.5 flow going to the rating 3. Meanwhile, element T2 has a full flow to move from T2 to the rating of 2 and no edges to anywhere else. So the optimal categorical ranking is finding a permutation matrix that maximizes the trace, that's the argmax of the trace, okay, of this permutation matrix for y hat. So we take our y hat and we're going to search over all the possible pathways. And what we're really saying is we're trying to maximize the flow possible from the left to the right. So of course, we would expect if this was 0.75 going to 1 and 0.25 going to 3, and this was 0.75 going to 3 and 0.25 going to 1, then the optimal ranking would be T1 goes to 1, T2 goes to 2, and T3 goes to 3. Now, in this case, there are multiple different rankings that are optimal. T1 could receive either of these ratings, and so we don't necessarily know what the optimal is. From this perspective, there's more than one answer. So I'm not going to go into this too much because it becomes a little bit of a hassle to talk through, but there's a Hungarian algorithm that's called the assignment problem. And the question is to find the min cost matching from items to labels. So if you have an item, you'd like to give it a label. Items, in our case, T1 through T5 to labels 0 through 5. And your job is to find, by choosing one entry from each row, that is assigning each element, T1, a label, find the minimum cost matching. And again, if it's minimum, you can always just transform it from maximum, which is the way I had been thinking about it, to minimum by doing 1 minus. And if you're interested in this, I really recommend you walking through it. The key is it has a process of deducing. You subtract the smallest value from each row, then you remove the smallest value from each column, and this iterative process arrives at the final result. And it's really really quite cool. But let's just take a moment, and what I really want to focus on in terms of our thought process is really about this graph that's right here. In what cases do we think that this categorical approach to rating rating actually makes the most sense? And in some ways, it's not too complicated, right? Often what we're thinking about is we're thinking about situations where we're going to be giving a set of elements ratings, and we think most of those ratings are broadly in sort of broad agreement, although there is some local disagreement. Right? So if basically everyone agrees that element 1 should be in element 1, but there's some disagreements, right? Element 1 has a rating that moves sort of in this space, and element 2 has a rating that sort of moves in this space. We could say that, again, in this case, Gaussian distributions over 5 elements. Even if an individual might not give you a rating or a ranking exactly the position that you want, it's not perfect. If we saw on average that mostly people were in broad agreement, then we're in a good spot to think that this approach is going to actually be quite useful. This also sort of gives us this notion that the items are really distinct. There's not a lot of situations where the items could be easily interchangeable, and that's quite important in terms of the ranking perspective. So, one of the first things that students will ask when we start thinking about rankings and ratings is, why don't we just take this probabilistic approach? This notion of elements have categories. Well, one reason that's very easy is you may have so many elements that it's very hard to calculate those probabilities, right? The number of websites on the internet is huge. It's very hard to calculate exactly what the ranking would be. The other that's potentially more important is that there are major disagreements in terms of what the best websites are to visit. And if there's not broad agreement, then your rank aggregation algorithm can cause real problems if you take this sort of probabilistic approach. Okay. So if that's our framework for thinking about categorical data and thinking about how things move along those lines, let's start thinking about this ordinal data. That is those relationships where we see A is greater than B is greater than C. So this binary comparison matrix, we can really take two approaches, and we're going to talk about what that means in terms of the binary comparisons. So lots of math on this page. So for binary comparison matrix, you can sort of have two frameworks describing this. You can have what's referred to as skew symmetric matrices. These are matrices where every Aij entry is equal to the negation of Aij. And so what we're really saying here is that for every entry that we had, and this is very much like what our matrix looked like, T0 is a 0, but T1, 2, or AI1, 2, this row is actually the negation of 2, 1. All right. And same thing across the whole board. Now, where does that leave us? That leaves us in a situation where a healthy matrix, and that is if I take one rater, I will note that in a binary comparison matrix, in a matrix of this form, not only does this hold, but for one rater only, I can take every AIK entry and say that's equal to AIJ plus AJK. Hold on that for a minute. Let's jump back over here to reciprocal matrices. Now, reciprocal matrix says that every Aij entry, every entry here, say, so it's a T1, T3, that it is equal to 1 over the value that's on the other side. So T1, comma 3 is equal to is 1 over this value that's here. So if I make this I and j, then this becomes j and I. That is 1 over this value gives me the value on this side. 1 over this value gives the value on this side. Now again, in this case, this similarity when we're talking about transitivity, that is the agreement, we can say, again, take one rater. Every rater individual AIK is equal to AIJ over AJK. This is not an easy idea to understand. I will not be able to explain it to you sufficiently in the course of this 1 hour conversation. This is definitely something that's left for you to think about and think about why this is. But I want to give you the important point of why that matters. If I have this row of relationships that run across, right? The distance from the first element to the second element and the distance from the second element to the third element is the distance from the first element to the third element. That is, one rater has agreement that item 1 is better than item 2 is better than item 3. And therefore, if you were to look and say, what's the difference between item 1 and item 2? And what's the difference between item 2 and item 3? That is the difference between item 1 and item 3. Because it's one rater. There's no disagreements. So we call that aspect, we call that relationship transitivity. That is, if I have item I that's 1 better than item j, and item j is 2 better than item k, then I needs to be 3 better than item k. This is the rating that you provided, and so it has to be true that I'm going to take I and I will move 3 down to get to k, or I can go through I to j and through j to k for the same total, the same distance. It has to be the same distance. Now note, we can construct this y hat on this left-hand side from the vector v. The vector v is the single user vector. Remember that first matrix, we take that one expression, item 1 is better than 2 is better than 3. We take that that single vector v, and we can multiply it by a row, by a column or row vector of all ones, and do a subtraction. This right here, this is a great thing for you to do on your own. 1, take that matrix 1, 2, 3, take the vector of the ratings, and try and construct using NP1s and a transpose and an NP dot multiplication and a subtraction to try to construct one of these matrices. Perhaps I'll do a little recording of that on the side as well. That would be actually kind of nice. Similarly, you can, instead of using the subtraction, you can do the same thing, but you can just use division. It's worth noting here that I can convert between my skew symmetric and my reciprocal matrices by using exponentiation or using a log. These representations, whether I choose to represent my data as a skew symmetric matrix or as a reciprocal matrix, only has an effect on the algorithms that I run at the next step. Before I run the algorithms, I can exchange between these two matrix representations the same. We're essentially saying the same thing here, but representing it in different styles of a matrix quite trivially. And again, the real important part here is this notion of transitivity, because I've said that when one person has a perfect ordering, we can construct a matrix of this form where this vector is the ranking, the ratings for that user. But if I put 2 or 3 users together, they're going to disagree on parts, and there won't be a perfect vector v that will generate a matrix of this form, or the matrix that I generate will have intransitivity issues. It will no longer hold that item 1 is always better than item 2 is always better than item 3. And that's really the heart of the algorithm that we're going to be getting to next. So if we understand this idea of binary comparisons, we want to move on to this different notion of 2 ways of thinking about these graphs. And this was, again, one of the things that I really wanted to think about was I didn't want to just think about, how we're going to run the algorithm, what the runtime is, things along those lines. I wanted to think about what cases we'd want to use these different approaches. So one is this notion of graph is given. So here, we take another question. We take a distance. We have one rater, rater 1. This gives us T1 is better than T2, is better than T3, is better than T4, is better than T5, 6, 7, 8. So we have this whole completely connected cluster with relationships indicating that T2 is in fact better than T6. See, T2 is better than T6. T1 is better than everything. See, we have directed edges. T8 has no outgoing edges. It only has incoming edges because it's the worst of all the items that rater 1 envisioned. Then we have a second node. Here, we have another dense cluster where we have a notion that T9 is better than all of the nodes seen by the rater on the right. T9 is better than 10, is better than 11, is better than 12, and is better than 1. So T9 directly dominates T1 according to rater 2, but T1 dominates a much larger cluster of elements according to rater 1. And the question we have to ask is, do we believe that T9 should be the top element, or do we believe that T1 should be the top element? And this gets to the heart of the question that we've been asking. So 1 is this inferred pass notion. This is our power iteration. The Analytic query process, Google's PageRank, they'll all think about network centrality. And if we imagine that this graph is a large network, as it is, a larger network, T1 is actually closer to the center of the graph. Even though it's not the top node overall, right? There are other elements that dominate it. It actually dominates a much larger set of nodes than the node on the right. So if we were to imagine this like a website, a graph of a website, we'd say, well, T1's the best website for 100,000 other websites. But the truth of the matter is, there's some small cluster of websites that specialists really think are great, and in those cases, they're actually they think their element, this T9, is actually better than all the other websites on the Earth, but they never look at the regular websites over here. They really just focus on these on the right, and you think, well, it's nice that those specialists think that, but that's not really germane to my average user. A great way of thinking about this is movies. If this is Hollywood, and T1 is the classic sort of blockbuster that's dominating all this and all those shows. I went to film school, and so at film school, we might not think that film is particularly good. We might think that's a bunch of avant-garde film, experimental film, claymation film from the 70s is actually much cooler. Well, it's all nice that we as a bunch of specialists have a certain set of opinions, but that doesn't mean that some of that work, brackage filmmaker is going to be exciting to the average person in the audience. Not at all. And so we really want to note that the idea here is that this greater dominance over a larger number of elements that T1 has is actually superior and more important to us than the fact that another rater saw that a small subset of these films and thinks that their genre is actually more interesting. Now, there's another way of saying this that's the inverse, which is just to say, heck, who am I to say that the fact that T9 is better than T1 and T10 is better than T1 and T11 is better than T1 and T12 is better than T1. I don't want to throw away that information. I don't want to lose those relationships. I want to really focus on the idea that explicit domination of that value is important for my problem. And these are the two approaches you can take. You can take the graph as given. You can say, look, the graph as it is, the decisions that were made tell us a lot about what those the relationships are. And I think this is the most intuitive in a place where I construct an environment where you have to do certain ratings. If I give you a set of ratings, say I want you to rate these 5 elements, and I give another 5 elements to another individual and say I want you to rate those. Then if you go and you look, you say, well, you never had a chance to look at what the best element was overall. You could only look at the elements exactly as you were given them. And that's this sort of notion the graph is given. I've constructed through my sampling process, through presenting you with elements, of a highly scripted, maybe even something that looks very much like this, where there's not a lot of opportunity. You'll never get to evaluate this value with this value directly. And so what we're going to have is just small regions where we might have some disagreement, but we'll have to construct this very long graph from the exact edges that were given, versus this notion of inferred paths. Now, why I think this is important, let's go back to our example with Hollywood. All of T1, all of these ratings, rater 1 who saw all of these videos could have watched the videos that are over here in our subcluster. And the fact that they chose not to watch those videos is an indication that the videos over here actually aren't that interesting to them. It's not just that they were rated. The lack of an edge is an indication of something. Think about how different that is. I sit down at my Netflix queue, I open it up, I look at 1,000 movies, I choose which movies I'm going to watch. So even if I make a rating that rates element 2 above element 4, it's implied, although not stated, that element 2 is more interesting to me than element 9, because I didn't watch element 9. I could have watched element 9, but I didn't. And that's the real difference in my mind. On the one hand, if you're running some sort of highly structured experiment where individuals aren't allowed to make their own decisions about what elements they rate, then this graph as given approach makes a lot more sense. Whereas, if you're working in a situation like the web, where you can go to any website you want, you can link to any website you want. Even if you rank something lower on the website list, but you chose not to list other websites, that's an indication of their lack of importance. And that distinction is really at the heart, in my mind, of why you might choose one of these approaches over the other, or why the results have some intuitive value. So now we have an idea of this graph as given approach versus this inferred path approach, and we're going to follow up on this graph as given approach on the left-hand side and follow up with Hodge rank, which I'll touch on very briefly. So Hodge rank is a really cool theory. It's mathematically super fun. There will be a link down at the bottom. We think they did, the presentation by the AMS, American Mathematical Society, is great. It's wonderful. It's very intuitive. But I wanted to just address one little piece of what's going on here. The first thing is this is Hodge theory, and it's just called Hodge rank. The key notion here is that there's this structure for Hodge decompositions that deal with different types. You have curl flow, gradient flow, and harmonic flow. So, the harmonic flow is kind of the bus, the wheels on the bus go round and round. A is this curl flow, which is the surface flows on the surface of a shape, and B is a gradient flow. This is used to decompose and describe physical objects, to describe geometric structures. So let's sidestep that for a moment and focus on what that looks like in terms of our exact example. If you remember from our early example of transitivity, we had this notion that if 1 connects to 2 and 2 connects to 3, then 1 should connect to 3 by the same distance. That's what we're trying to do. In fact, we know that when we take a variety of different users, we aggregate their results together, I might say element 1 is better than element 2. You might say element 2 is better than element 1. We have a disagreement. There's an edge. There's a circle. And so if we look, because we only did 2 in that steps, that would be a global flow. But let's just look at this and note in this particular example of these relationships, we would add together our matrices just like we did at the beginning to find some agreements. And we see that element I is 1 better than element j, and element j is 3 better than element k. But element I, in my matrix, same again, my matrix that I constructed, element I is 3 better than element k. This doesn't make sense. If the distance from I to j is 1, and the distance from j to k is 3, the distance from I to k should be 4. But it's not, it's only 3. And so we refer to this as the triangular flow. This is, effectively on the surface of the object, there is a disagreement from what you would expect for transitivity. Similarly, if we look at I to k is 3, and from k to L is 2, and now you note that from L to I is 3, that's what we wouldn't expect at all. We'd expect that the distance from I to k would be 3, and from k to L would be 2, and then finally the distance from I to L would be an edge in the opposite direction, which would equal 3 plus 2 should be 5. And so this is what we refer to as global flow. And the goal here, the goal of Hodge rank, is to remove both the triangular flow and the global flow so that we have a single ranking that works, that we have the case of transitivity. So now we're going to use a little matrix notation. That is Y bar. Y bar is our aggregation of all of the raters. So you take each rater and you construct it into one global ranking. Remember at the very earliest slide, we saw that we had rater 1s and rater 2 that constructed Y bar. We can imagine that Y bar is made up of 2 types of matrices. A matrix that is consistent, and that consistency matrix is a matrix that has transitivity. It has the aspect, in this case it would go I to k would be 3, and k to L would be 2, and then I to L would be 5 in this direction. That matrix would be transitive, and that matrix would be consistent. And then we have kind of the noise or all the disagreements, and we'll call that the inconsistent matrix. So we know there exists some matrix that is consistent that would sort of iron out the disagreements and the wrinkles that are occurring here. And if we take that matrix and we add to it whatever the noise is, we could reconstruct our matrix Y bar. In fact, there are many matrices that are consistent, and there are many matrices that are inconsistent. And our job is to say, again, this consistency matrix is of that form that we introduced earlier, raters times 1's transpose minus a row vector of 1's times R transpose. But what we really want, this is the part that really matters, we're going to say what we really want is to find the smallest inconsistency matrix. Okay, so why would we do that? If I say I have a consistency matrix, but I have a really big inconsistency matrix, or I have one that has a very small amount of noise, so I have another plausible. If we think of all the different consistent matrices and their corresponding inconsistent matrix, if I gave you the choice between one consistent matrix that had a lot of noise, said, well, or another matrix that was just as consistent, but it had a small amount of noise, you'd choose the consistency matrix that had the smallest amount of noise. You'd say, well, I don't want to, I want to make sure that I get the most signal that's there and then extract just the small amount of noise of all the possible choices. So I'm going to look through all of the inconsistency matrices and find the one that is the minimum. There's a Frobenius norm. This is the same thing as what we're trying to do in a least squares scenario. If we go back to least squares, we say, what are we doing in least squares? I want to find a line that minimizes all of the error. So what does this matrix U look like? It's, in fact, we can subtract because we can just, with substitution, come over here and note that if I want to have U, I can just move C from this side to the other, and I can say Y bar minus C. It's of this form. So now what I've just come up with is I can take the original I can take all of the y bars, that is the final matrix, the aggregation of everybody, and subtract all the different consistency matrices that I can find, and whichever one creates the smallest noise, the sort of smallest imprint, that is what I'm looking for. That is the one that I'm looking for. And ultimately, if my consistency matrix is if the consistency in my aggregation of all of these different individuals divided by the total size of the matrix is pretty big, in fact, it's much bigger, that's what these double bars equal, than the size of the inconsistency matrix, then there's, it's pretty clear things are in agreement. So if, we went back and we looked at that original matrix where we sort of aggregate people together in terms of if we think about a matrix where mostly people are in agreement and a small number of people aren't in agreement, then we would imagine that this condition would hold, and the consistency matrix, the matrix that has transitivity, we would probably trust. If this were not the case, then we'd be saying there's too much noise in the system, there's too much broad disagreement. And I have barely touched. The original Hodge rank paper is a tome of great literature. It's worth reading. It's worth looking at. It's very interesting in terms of its theory. It's very cool. Now we're going to move on to AHP, and we're going to just touch briefly on AHP. Today, I probably wouldn't present this as AHP. I probably would present it as PageRank. One of the advantages of talking about analytical hierarchy processes, everybody knows about PageRank. People don't realize that Sathe had been working on this work previous to PageRank becoming dominant. He's got a couple of neat tweaks of the way that he thinks about things, but you can, sort of from the perspective of students in 2021, which is when this is being recorded, you can think of this as being, pretty similar to what we think about in terms of PageRank. So we're going to talk about that. So AHP, and it's probably, I should find the best link for this as well and drop it in the show notes, but the goal really is to collect survey on some kind of multiplicative scale and then do paired comparisons between elements. So the idea here was that you'd collect data, you'd calculate by establishing the largest eigenvalue for the corresponding eigenvector. This is exactly what we do in PageRank. And then you'll evaluate that accuracy. Now the last part is kind of important here. We talked about in the first case, we have this, if the consistency matrix is much larger than the inconsistency matrix, we trust it. This is the same thing that HP is trying to do. And again, accuracy is probably is the incorrect word to use in this, but he uses the term consistency index, and that's probably more appropriate. So the consistency index is this lambda max divided minus n over n minus 1. Again, I don't want to get into the way that Sathe establishes the expected consistency index, other than to say this. The base premise today is most relevant to what we consider to be random matrix theory. That is, if you were to take a random matrix, what would you expect the eigenvalues to be? And there's really neat work that's happening right now with a product called Weight Watchers that comes out of, that's very cool. I've had a little chance to play with some of these tools, but the assumption here is that as we're training models, we'd like to use random matrix theory to describe what we expect random structure to look like, and that's exactly what this is. Sathe's consistency, he's calculated expectation of what random disagreement should or shouldn't look like, tells you that if the consistency ratio, that is the agreement within your group, the consistency index within your group, divided by this number that is the number that we'd expect to occur by random assignment of values. If it's a very small value, then we can sort of accept those results. So what he's really asking, although, again, the mathematical justification of it we'll set aside for another lecture, what he's really asking is, can I look at the data as presented and say that it varies significantly from what a random process would generate? And if it varies significantly from what a random process would generate, then I will accept those results. Okay. And that's actually not a crazy, that's a pretty straightforward and reasonable way of approaching these kinds of things. It's not a crazy assumption at all. It's actually a really useful one. And we see it occur over and over again. The notion is, if something were just to happen on its own randomly, what would that look like? And since this doesn't look like that, then probably there's a real value to what we're looking at. It's a nice basic framework. So in my case, we're going to touch on a couple of different things just for very briefly. More importantly, we'll start with this wine ranking. There's this judgment of Paris. It's from 1976. And really what was required was that they had a collection of wines and a collection of raters. And the question was, what is the top wine in the rating? And this was really important because for the first time an American wine won, and this really changed the wine industry. And you can see that, in fact, Stag's Leap won from 2000 with a value of 14.13, so just barely beat out a French wine for the second rank position. And the first thing that, and this was even recognized in the 70s, they released this result that made international news. Lots of money flooded into North America for wine production accordingly. But even at the early days, when they were asking the questions of was this a reasonable way of calculating or tallying the results, the people who were tallying these results didn't have deep mathematical knowledge. They didn't come from a mathematical background. You can see on the right-hand side that the average score for each individual varies. So, from as low as, 9.2, the average rating for this individual said these wines were only 9.2, and the highest rating went as high as 13.5. So what this is telling you is that the scales weren't normalized. Right, things weren't normalized, and so the relative values weren't preserved. And because of that, even from the very beginning, there was great question as to whether or not the final results worked, because you could very easily skew this result by just knowing that if you rated the wines, a greater extreme one way or the other, you would have a larger outsized impact on the overall rating. And so we can look through here and see what the individual numbers is. The hard part of this is, given this whole block of data, because it is a block of data, what kind of questions do you ask? And students will typically think about asking sort of iterative questions down a certain line, what's the average rating for this one and all the rest. So what we're going to do is we're going to apply these three different approaches. And so to start with, I said a long time ago, if you think about these ratings as being based on, if there was broad agreement on the rating positions of what each of the wines should get, then you would see that there would be these kind of like Gaussian distributions. And in fact, you do see certain things. You can see that Aubryon is definitely sort of shifted to the left, and Montrose, again, to the left as well, and Lacasse here to the right. And we've got almost like a bimodal distribution here, and Rothschild here on the left-hand side to the right. This is almost even. This is, maybe almost even, but a little bit more to the right. You can see there's some debate, and you could quibble with my arguments here. We see that Stag's Leap, in fact, does look to the left. And we see that, if we were to look, the Stag's Leap actually looks like it is doing a little bit better than Rothschild, but just by a little bit. Not a huge amount, and not so significantly that we think there's a definitive sort of slam dunk. So what I did was to take, in this case, we're not working with the raw scores, but we're working with the rankings. That was one way to address some of the questions about non-normalization of the actual exact ratings. And so you have each number is the number of votes per position. So Aubryon, come over here, we look at Aubryon. Aubryon had 3 votes for position 1, and had 1 vote for position 2, and had 3 votes for position 3. And now we look and we see the yellow is, let's start with the green. Green is a historical rating. That is, Aubryon was ranked 4th in the historical rating, and yet it only received 1 vote to be in 4th. It, in fact, received, the vast majority of the votes were higher, 3, in terms of the ratings, in terms of how the relative rankings were. If you used the Hungarian algorithm, the approach that I was talking about from my master's work, you'd find that the Hungarian algorithm would have placed Aubryon in 3rd position. And similarly, you can see that Rothschild historically placed in the 2nd, and Hungarian algorithm would have rated it a little bit lower, would have rated it in the 4th position, and so forth and so on. And the most important point here is I never had to make a graph where the Hungarian algorithm and the historical rating would align. They were always in disagreement. Okay. So if we think, again, this is a way of thinking about what the, sort of each position votes for. And this is fascinating in the sense that here, these elements that ranked very low, whoever placed them 3rd, that vote sort of just disappears. Now we can take the same ranking and we can do this for Hodge rank. And what we can find, again, by creating the y-hat matrix, right? That's the aggregation of all the ratings together using this data set here. We take each rater and aggregate them together. And we end up with a consistency matrix that looks like this. Don't even try and interpret it or try to read it very densely. And an inconsistency matrix that looks like this. And we can see, I've plotted this out so you can get a sense of the edges is where they go to the individual positions. And then a heat map to show you where the relationships are, what's dominating. And what we see, again, I use the word accuracy. That's not the right word. We should say consistency. The Hodge rank gives us a consistency of 0.73, which isn't terrible. That's actually a pretty good number. And we see that first position is Stag's Leap, and then tied for first was Montrose. We actually had a tie between the two top ratings, and Rothschild placed third. And you can go down this list, and this is the historic rankings in terms of the order. So we see that the second position was actually placed third. The third position was bumped up to tied with first. But fourth and fifth, sixth, there's some changes in here, seventh, eighth. We see we have a tie for 5. So broad agreement in general, but there are definitely changes along these lines. And then we can use AHP to do something similar. Again, the consistency ratio here is 1.58. The conclusion, and this is probably the graph that sums up the most, again, not so much accuracy, but rather consistency, is that the 1976 had this value of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hodge rank gets places this Stag's Leap in second. Hungarian algorithm places it in second. Hodge rank places it in first. AHP places it in second. You can see that there are very few moments where there's agreement. Maybe not very few, but there's fewer moments of agreement. Lots of moments where the individual algorithms disagree. And one of the things you have to ask yourself is, if that's the case, how do I make a decision between each of these individual algorithms? You can't just calculate the final prediction, use this particular metric, which is individual to each algorithm, right? Each algorithm has its own sort of consistency matrix, consistency ratio. You can't just compare them one to the next and say, well, this is a 2.26 and this is a 0.73, so I'm going to choose the 0.73 or I'll choose the 0.26. We don't know that. That isn't written in stone. And this gets back to the question, really, of where we started the discussion, which is, since there's no grand description of what the optimal choice is, how do we choose between these algorithms? How do we choose along those places? And the goal, really, in terms of my talk, was to give us some sort of framework for thinking about why that might be the case, based on the kind of assumptions we have about the data. And then this is almost impossible to read, but what I also did for my work was to scrape, you can't quite see at the top here, but US News and World Report ratings, the higher education, QS, is multiple different ratings over multiple different years, and it's a tremendous amount of data. Forbes is 6 years, higher education is 4, 10, and 12. This was a huge amount of cut, scraping, PDFs, and everything else, to come up with a ranking, in this case for college rankings, which doesn't lead to a lot of changes, but except that you might see that some things like Harvard do very well consistently overall, but you see some intransitivity or some movements across different places. So with that, I think we've hit the end of the talk, and I just want to leave us perhaps with this slide as the most important, because you're going to be in situations regularly in your professional work where people are asking you to take together a collection of ratings, a collection of elements, and present them to a user. And you may have a variety of different ways of doing that, a variety of different ways of aggregating from different sources. I don't have a great answer, and I don't think there is a great answer for the optimal way of doing that. But I do think that the most important thing you can do is to think deeply about the way that you're generating the data. If users are left out on their own to make their own decisions, and they've sampled, and those samplings imply something about what they'd actually like to do, food, restaurants, those sorts of things, then as we move, Netflix, of course, news sources, things along those lines, then we can trust. We can very likely trust, we can have greater confidence that the data that we're working with can use these network centrality, these node centrality measures, because we believe that the users have made decisions based on their understanding of all of the choices that are available to them, and they've chosen to go through and read and engage with the material that's important. This video, for instance, if you made it this long, which probably 3 of you have, but if you have made it this long, that tells a lot about kind of what you want to spend your time doing. Similarly, if we're in a situation where we have a highly scripted environment, where we are only allowing a small number of people, we're only allowing access to a small collection of choices, and then trying to assemble those choices into a larger sort of scaffold of ratings, then we're much closer to the framework that I described earlier with a Hodge rank where we're thinking about exactly what the ratings are, and we want to sort of construct this very long, I like to think of it as like a ladder, a trestle, where individual items are ranked. And then finally, if we think that what we're doing is something that, we're taking 1,000 elements and we're going to score them really on a scale of only 1 to 5 or the top 25 results, then maybe that's a different system altogether. And we haven't even talked about the idea of focusing different parts of ranking on different portions of the graph. Most of the time, places like Google, places like Facebook, they really are interested in giving you results just at the top of your search listings. They don't care about what the 10,000th or 100,000th entry is. They care what the 1 through 10 is, and they spend a lot of time trying to identify those optimal choices. Deep learning has given us a whole bunch of new tools that allow us to think more deeply about the context of the individual, the context of how the ratings have occurred, getting more nuance about what we think, how to think about comparisons. And there's lots more work we can do along these lines. But something that seems so simple, which is just we're going to take some elements, we're going to take some people's opinions and just sort of aggregate them together, as you can see, blows up into a very complicated problem as you start to look under the hood. And that's why I think this work is still quite exciting. And if you like this work, I'm still working on deep reinforcement or deep learning approaches to recommendations today that are directly applicable, because we'd like to use a more rich context vector that describes the individual, or a better understanding of the underlying data. That is, maybe there are clusters within our original data sets that describe different styles of wine, and we'd like to see how those clusters actually fit into the overall process to rank new wines that we've never been exposed to. So it's both a process of ranking existing results as they are, and thinking about ranking elements that we've never seen before and trying to figure out where we think they will fit in so we can follow whatever process we like. And if at the end of this you feel like the sort of certainty that you would expect for in terms of machine learning is gone, that is, it's very relative, it doesn't feel like there's one particular right answer, you are 100% in agreement with myself, you're pretty much in agreement with everyone. There's a high amount of flexibility that we can use and a lot of discretion we have as machine learning researchers into which algorithms we use and how we use them. And when we think about bias and we think about problems occurring within the algorithms where the algorithms don't give the expectations that we would hope for, this is just one opportunity for where these sorts of things can sort of sneak into the overall discussion. Anyway, I'll leave it at that. Interested to hear your thoughts. Feel free to ask any questions at the bottom, and I will try and hit up the comments section. Thanks so much.